the recording. I always put it on pause when I start, so I just started up. Okay, very good. So again, the negation of an existential statement. It's not the case that there exists at least one element in D such that the property Q of X is true. That's logically equivalent to the statement for all elements X in our domain, the property Q of X is not true. And again, the negation of a existential statement, some are, is logically equivalent to the universal statement, none are, or all are not. So take a minute and write the formal negations for A and for B, a universal and an existential. Yeah. Okay, let's take a look at these. The first one, for all primes P, P is odd. So this is a universal statement. And by applying the rule for the negation of a universal statement, we can see that the answer is there exists an element A that's prime such that A is not odd. Or we could say there exists a prime P such that P is not odd. This is, again, following the rule for negation of a universal statement. We take the existential of the negation of the predicate. For B, which is an existential statement, by applying the rule for the negation of an existential statement, we can see that the answer is here for the existential statement. There exists a triangle, T, such that the sum of the angles of T equals 200. So the negation of that is going to be for all triangles T, the sum of the angles of T does not equal 200. Yeah, I'll go ahead and write that out. So we'll take our existential statement. These the negation of that, and the negation of that's going to give us Okay, and we'll take the first one also. This is B. And here's A. And the first one is for all primes P, P is odd. Okay, so for A, our universal statement was for all prime numbers P, P is odd. We want to take the negation of that, which means that there's going to be, for a negation of a universal, there's at least one exception. So the negation is going to be, there exists a prime number P such that P is not odd. And then for B, we have our existential statement. There exists a triangle T such that the sum of the angles of T is equal to 200 degrees. So we take the negation of that existential statement, and we're going to get a universal statement. For all triangles T, the sum of the degrees of the angles of T is not equal to 200 degrees. So we take the negation of an existential gives us a universal. The negation of a universal gives us an existential. Okay. Okay, let's get chat back up. Yeah, I just wrote out one of those. And somebody's in the waiting room. Them in. Okay, again, any questions on what we've covered on the negation of universal and existential statements? We've written out two examples, one of a universal, the negation of a universal, and the other, the negation of an existential. Okay, let's go on and we'll look at negations of universal conditional statements. So, of course, the conditional statement has the form for all x, if P of x is true, then Q of x is true. Okay, a couple of people joining the class. In the last example, A was the negation of the universal and B was the negation of the existential. Okay, and that one. So now let's look at the negation of a universal conditional. This is a special importance in mathematics, as was said in the last lecture. This universal conditional statement is widely used in proofs. So naturally, the negation of it would be widely used in proofs as well. So we have what we're looking at, the negation here of our universal conditional for all x. If P of x is true, then Q of x is true. that's logically equivalent to an existential statement that we have at least one X such that it's not the case that if P of X is true, then Q of X is true. Now, if you'll remember from chapter 2, the negation of this conditional is going to be logically equivalent to there exists an X such that P of X is true and Q of X is not true, or in other words, not Q is true. So we can substitute that into our statement, and we get the another logical equivalence, and that is the negation of for all X, if P of X is true, then Q of X is true, is also logically equivalent to the existential statement. There exists at least one X such that P of X is true and not Q of X is true. And we see that in the negation, in the blue box, the negation of a universal conditional is going to be the existential of a conjunction, P of X and not Q of X. Okay, so take a moment and write out the negations of these universal conditional statements. And we'll go over those in just a moment. So go ahead and work through these two examples. Okay, let's take a look at these. For A, we have the universal conditional statement for all people P. If P is blonde, then P has blue eyes. So the negation of this is going to be an existential statement, and it's going to be a conjunction. So it would be there exists a person P such that P is blonde and P does not have blue eyes. For the second statement, we have the universal conditional. If a computer program has more than 100,000 lines, then it contains a bug. And so Here, the negation of that informally, which was what we were asked to give for B, is there's at least one computer program that has more than 100,000 lines, and it does not contain a bug. Okay, any questions? Okay, and I'll definitely write those up as well. Okay, the first one, and B, okay, so let's take a look at these. So the first statement, A, is the universal conditional for all people P. If P is blonde, then P has blue eyes. The negation of that is going to be an existential, that's a conjunction, and it's going to be the conjunction P is blonde, if this is true and this is false, and P does not have blue eyes. So formally, that is, there exists a person P such that P is blonde and P does not have blue eyes. For part B, we have the universal conditional. If a computer program has more than 100,000 lines of code, then it has a bug. The negation of that is again going to be a conjunction, in other words, an and statement. And it asks us to give an informal interpretation of the negation, and that is this. There is a program such that the program has more than 100,000 lines of code, and the program has no bugs. Okay. Let's go on and consider some more about the relationships between For all, there exists our conjunction and our disjunction or. So the negation of a for all is there exists, and likewise, the negation of a there exists is a for all. This is analogous to De Morgan's theorem, where the negation of an and statement is an or, and the negation of an or statement is an and. And this similarity is not accidental. In a sense, universal statements are generalizations of and statements, and existential statements are generalizations of or statements. So let's take a look at that. So here we have a universal statement. For all x that's an element in D, Q of x is true. So what that is really saying is that if we plug each element x, meaning x1 through xn, into our predicate, it ends up being true. So it's logically equivalent to Q of x1 is true, and Q of x2 is true, and so on through Q of xn is true. And similarly, if Q of x is a predicate and we have the existential statement, there exists at least one element in our domain such that Q of x is true, we can see intuitively that that's equivalent to Q of x1 is true, or Q of x2 is true, or all the way through Q of xn is true. At least one of them has to be true for the existential statement to be true, whereas for the universal, every one of them has to be true. So there is that equivalence between De Morgan's theorem and what we see in universal and existential quantification of statements. So let's look at another thing. When we were talking in chapter 2, we talked about the vacuous truth, and that is if in a conditional statement the antecedent is false, then the statement was going to be true. And let's take a look at this in terms of the negations. So let's consider that we have a ball that sits on a table, and we have three blue balls and one gray ball placed in the bowl. Then the statement all balls in the bowl are blue would be false, because there's at least one ball in the bowl that is gray. Now let's suppose that we take all the balls out of the bowl. Then we want to consider the statement, all the balls in the bowl are blue. So we have to consider, is this statement true or false? Well, it's false only if its negation is true. And the negation in this case of a universal statement and all statement is there exists a ball in the bowl that is not blue. So we had the universal statement, all the balls in the bowl are blue. The negation of that statement is there exists a ball in the bowl that is not blue. But the only way this negation can be true is if there is actually a non-blue ball in the bowl. And of course there isn't, because there's nothing in the bowl. So the negation is false. And so we say the statement itself, the universal statement, is true by default. And this is also called vacuously true for universal conditionals, just as it was for our conditionals. So if we have a statement of the form, for all x in D, if P of x is true, then Q of x is true, it's vacuously true if and only if P of x is false for every element in D. Okay, let's look at our usual suspects in terms of the variants of universal conditional statements: contrapositive, the converse, and the inverse. So we've gone over these in chapter 2, and we'll go over them again here. They're going to be intuitively obvious. So again, we have conditional statements that have a contrapositive, a converse, and an inverse. And those definitions can be extended to universal conditional statements. So if we have a statement of the form, for all x in D, if P of x is true, then Q of x is true. Its contrapositive is the statement, for all x in D, if not Q of x, then not P of x. That's the contrapositive. The converse is the statement, for all x in D, if Q of x is true, then P of x is true. And its inverse would be, for all x in D, if not P of x is true, then not Q of x is true. So let's get some practice with contrapositive, inverse, and converse in a universal conditional. So write a formal and an informal contrapositive, converse, and inverse of the following statement. If a real number is greater than 2, then its square is greater than 4. So take a minute and write down those example variations of our statement. Yeah, and I'll go ahead and write these up as well while you guys are working on them. Okay, let's take a look at these. So our statement is going to be formally for all x that's an element of R, the real numbers, if x is greater than 2, then x squared is greater than 4. That's our statement. Then the converse is going to be for all x that's an element of R, if x squared is less than 4, if x squared is less than or equal to 4, then x is less than or equal to 2. And we could say this informally as if the square of a real number is less than or equal to 4, then the number is less than or equal to 2. The converse is going to be for all x that's an element of R, if x squared is greater than 4, then x is greater than 2. And informally, we would say if the square of a real number is greater than 4, then the number is greater than 2. And then the inverse is going to be for all x that's an element of R, if x is less than or equal to 2, then x squared is less than or equal to 4. Or if informally, we could say if a real number is less than or equal to 2, then the square of the real number is less than or equal to 4. Okay, and then to show visually, this is our statement right here. For all x, it's an element of R, the real numbers. If x is greater than 2, then x squared is greater than 4. The contrapositive of that, by definition, is this statement. For all x that's an element of R, if x squared is less than or equal to 4, then x is less than or equal to 2. The converse, again by definition, is for all x that's an element of R, if x squared is greater than 4, then x is greater than 2. And then finally, the inverse for all x that's an element of R, if x is less than or equal to 2, then x squared is less than or equal to 4. Okay. Okay, so if we have P of x and Q of x are some predicates, then we consider our universal conditional statement for all x that is is an element of the domain D. If P of x, then Q of x. And then we have its contrapositive of for all x that's an element of D. If not Q of x is true, then not P of x is true. So what we're saying there is that this is going to be true by the logical equivalence that we established in chapter 2 of if P then Q is logically equivalent to not P then not Q. So here we see the formal equivalence of the two statements of a statement and its contrapositive. So again, it follows that if P then Q is true for all D, that's going to be true if and only if not Q, then not P is also true for all D, for all our elements in D. So we can write that formally as an equivalence our original statement, the universal conditional, for all x that's in the domain D, if P of x is true, then Q of x is true, is logically equivalent to for all x that's an element of D, if not Q of x is true, then not P of x is true as well. Now, let's look at the converse statements. So we had our statement that we just considered. For all x, it's an element of the real numbers. If x is greater than 2, then x squared is greater than 4. The converse of that, by definition, is for all x that's an element of the real numbers. If x squared is greater than 4, then x is greater than 2. But that's not the case because, for example, -3 is squared is 9. That's greater than 4, but -3 is less than 2. So from this, we can conclude that a universal conditional statement may have a different truth value from its converse. So what we say formally is that a universal conditional statement is not logically equivalent to its converse. Okay, and let's finish up with necessary and sufficient conditions for universal conditional statements. So we talked about necessary and sufficient conditions, and also only if conditions in our discussions in chapter 2 on logical operations and Boolean algebra. And we can those definitions to the universal condition as well, universal conditional as well. So if we have a statement for all x, R of x is a sufficient condition of S of x, that means that we can say for all x, if R of x is true, then S of x is true. That's our sufficient condition. And likewise, we can say for a necessary condition, for all x, if R of x is a necessary condition for S of x, that means that for all x, if not Rx is true, then not S of x is true as well. Or equivalently, using the contrapositive, we can convert that to say for all x as a necessary condition, for all x, if S of x is true, then R of x is true. R of x being then a necessary condition. And then finally, for all x, R of x only if S of x means that for all x, if not S of x, then not R of x. And again, using our contrapositive logical equivalence, we can say for all x, if R of x is true, then S of x is true as well. Okay, let's take a moment and write down the rewrite these following statements, and do not use the terms necessary or sufficient. Yes, that's right. They are. It's just two different ways of saying the phrase. So a lot of times you're going to be translating from an informal language like English into a formal language like Boolean algebra, and so you'll run into different ways that things are said, even though they are equivalent. Write these down. Okay, let's take a look at these. The first question A, we want to write a quantified conditional statement without using the word necessary or sufficient. So the first one is squareness is a sufficient condition for rectangularity. So a formal version of that statement would be for all x, if x is a square, then x is a rectangle. And informally, we might say if a figure is a square, then it is a rectangle. And then for B, so being at least 35 years old is a necessary condition for being president of the US. So here we could say for all people X, if X is president of the United States, then X is at least 35 years old. And then visually, we can say, again, for A, for all X, if X is a square, then X is a rectangle. And for B, for all people X, if X is president, then X is greater than or equal to 35. Okay. So, any questions on what we've covered today in quantification of universal statements, looking at the negation, necessary and sufficient conditions, things of that nature? Oh, yeah, hold on. Oh. Got it? Okay. Okay, so Tuesday we'll go over homework 2, and then we'll continue our discussion about quantification. It'll be out next week. Yeah, midterm exam is actually 2 weeks away, if I'm not mistaken. And by the way, I did get confirmation. Well, we'll go over that. I mean, it's going to be, you know, if you know the material in the lectures, you're going to do fine on it. But we're going to have a formal study session for the midterm, and it'll lay out everything you need to know to do well on the midterm. And what I could probably do, and I'll have to check the website, is I'll put the PDF that's the review guide for the midterm up there right now. So if you want, you can begin reviewing it. The other thing I wanted to say is I did get confirmation. We are off that entire week for spring break. So we have both those days, Tuesday and Thursday, off. And that is, in fact, now reflected in the schedule. And let's take a look at, I have the midterm on Thursday, March 11th. Tuesday, March 9th, we're going to have that formal review that I told you about. And again, we're going to lay everything out. And then next week, which is March 2nd and then March 4th, we're going to go over more quantification. This time, it'll be statements with multiple quantifiers. And then we're going to look at the validity of quantified arguments. Yes. Yeah, you're not going to see anything on the exam that you haven't seen conceptually in class. And then both Tuesday, March 16th and Thursday, March 18th, those are both spring break days. Okay. See you Tuesday. We'll go over, thank you, you too. We'll go over homework 2. Okay, thanks. See you guys Tuesday.
Professor, could you post the videos?
Yes, I am. I'm going to post the one sometime this afternoon, and then today's will probably be up tomorrow.